Let's take a look at this confidence interval problem. In a random sample of 200 adults, 150 of them prefer to use credit card as primary method of payment. This study is interested in the population proportion of adults who prefer to use credit card as primary payment. So let's do the setup. So how do you know this is a proportion problem? The reason is simple. There is no mean, variance, or standard deviation, right? You have a sample size 200 and then the number of success is 150. So the sample proportion is 150 divided by 200. You will see that I wrote all the setups on the right. I have the formula first, and then the sample proportion is x divided by n, which is 150 divided by 200. So that is equals to 0.75. So when you do all the works on your calculator, it is not necessary to put the proportion in decimal. Write this down. It is better that the problem gives you the sample proportion in fraction. Again, it is better, way much better, that the problem gives you the sample proportion in a fraction, not a decimal. If that is a decimal, then you have some work to do. And then I also check the condition. So when n times p hat is greater than 5, n times 1 minus p hat is greater than 5, then we say the sampling distribution of p hat follows normal distribution. Do you see the green? Follows normal distribution with the mean equals to p hat and the standard deviation. You can call that a standard error, the square root of 0.75 times 1 minus that divided by 200. All right. And then the next thing that you will have to do is you have to construct a 90% confidence interval. So let's go straight to our calculator. You have to go to stat, and then you go to test. Where is 1 proportion z interval? In my calculator, that is in line 8, the letter A, just right below 2 sem t in. So go look all the way down. Do you see that 1 prop z int? 1 prop z in, 1 proportion z confidence interval. And then you go inside, simple menu, they ask you for x, so we have 150 success out of 200 sample size, and then the C level is 0.90, and then you calculate. So this one usually for the decimal, you can keep 4 decimal places. I prefer to do that in this problem, so let's just write this down. 0.6996 comma 0.8004, right? And then for proportion problem, you can put this as a percentage. So how about 70%? And how about this 180%? So that is much simpler and cleaner, right? So what does that mean? That means we are 90% confident. We are 90% confident that the true proportion, what is true proportion? The true proportion means the population proportion, P of adults who prefer to use credit card. I'm trying to copy right here. Who prefer to use credit card as primary payment falls between 70% and 80%. So what does that mean? Let's make the language simple. So that means we don't know what the population proportion is. Confidence interval is a method of inference. Inference means we are trying to guess what the true proportion is. And then we have 90% confident that the true proportion P falls between 70% and 80%. So that's how we interpret this problem using simple language. And then other than that, when you do this, when you do a problem from a textbook or you do your homework online, usually they will break this down into little steps. So one very famous thing that they will ask you to do is they ask you to plug in the numbers. So to plug in the numbers, we have a 0.75, right? Let's do that. So we have 0.75. So that is p hat plus or minus z. So z alpha divided by 2 times the square root of p hat, and then 1 minus p hat divided by n, right? And then they also ask you to sketch the graph. So let's sketch the graph too. So here is my graph. We draw a normal curve. And then 90%, so we have the area is 90% right in the middle. Then how much do we have left? Then alpha is 10%, right? That is the remaining area. So we have 5% on the left and 5% on the right. So 5% on the left and 5% on the right. So this is my z, and then this is my z. So what is the corresponding z value of the 5% area on the left? So the z is equals to inverse norm, not inverse t, inverse norm. So inverse norm, and then you have alpha divided by 2. Either you input 5% or you input 10% divided by 2. The mean is equals to 0. The standard deviation is equals to 1. Inverse normal distribution, I will already talk about this when we are talking about normal distribution and the central limit theorem. If you don't know what it is, if you have no idea what inverse normal distribution is, you have to go back to watch those videos. So we go to second vars, and then we do inverse norm, 10% divided by 2, or you just type 5%. The mean is 0. The standard deviation is 1, so that is 1.645, right? So that is 1.645. So this is 1.645. So that's how you do the plugin. And then one other thing that they ask you to do all the time is called the error bound, or the margin of error. So how big is the margin of error? So this is called the margin of error, or you call this error bound. So how do you compute that? You do 1.645, look at my calculator, and then you multiply square root, second, and then you type the x square key to get the square root, 0.75 times 1 minus that, which is 0.25, or if you are so lazy, you can type this 1 minus 0.75, that works too, and then divided by 200. So the error bound is equals to 0.050, right? So to calculate the confidence interval step by step, you take 0.75 and then you plus or minus 0.050. That gives you the lower limit and the upper limit. So that is how the problem asks you to do it step by step. And then, okay, so that will be the end of this subproblem. And then in the next subproblem, what they ask me to do is they ask me to construct a 99% confidence interval. So let me take this to the next problem. So I am going to take this problem, take this expression to the next problem. I copy that first, and then in part B, so I'm going to do part B right here. So part B, they ask me to do a 99% confidence interval. Okay, so we go to stat test, and then we choose line A, letter A, 1 proportion Z interval. I don't need to change the X and N, except the last line I have to change that to 0.99, and then you calculate. So this is a 0.6711, comma 0.8289, and then put that in percentage. That is a 67%, and then this one is 83%, right? So how long is this? So the length is equals to 83% minus 67%, and then you also need to do this for the 90% confidence interval, right? So you take 93 minus 67, that is equals to 16%. And then the previous problem, so the 90%, I use, what color did I use? I use orange, right? Okay, I will follow the color code. So for the 90%, how long is the interval? The 90%, so that will be 80% minus 70% equals to 10%. So the 90% confidence interval is shorter. The 99% confidence interval is longer. What is the reason? The reason is, so let me paste this. So this, the blue we have, this one is from 90% confidence interval, right? So what about a 99% confidence interval? What is my Z value for the 99% confidence interval? Everything else, they won't change. So let's take a look at that real quick. So for the 99% confidence interval, the alpha is equals to 1%, right? And then for the z, so that will be z is equals to inverse norm. You take the 1% divided by 2, and then mean is 0, standard deviation is 1. So let's get that real quick. Second was inverse norm, you have 1% divided by 2, mean is 0, standard deviation is 1. So you have 2.576. The reason I ignore the minus is because the formula already take care of the plus or minus for me. So what do you see? Compare the z value. So for the z value, what we see is if you use a higher confidence level, you get a bigger z. As a result, you get a bigger margin of error, which is everything on the right hand side of the plus or minus. As a result, you get a longer interval, longer confidence interval. What if you reduce the z level? If you reduce the confidence level, just look at the blue, you have a smaller z, right? Just look at the blue z. And then as a result, you have a smaller margin of error. As a result, you have a shorter confidence interval. And this is true, what I wrote right here. The two conclusions I drew is true for any confidence interval for any procedure. They are always true. If you raise the confidence level, you get a longer interval. If you reduce the confidence level, you get a shorter interval. Another way to interpret this is if you want a higher confidence level like 99%, you want 99% of the interval to capture the true mean, right? Of course, you need a longer interval to do the job. Versus if you want like 50% confidence interval, you only want 50% of the interval capture the true mean, so a smaller interval will be fine. You don't need to make the interval so long, right? So that is the lesson we learned from part B. And then in part C, I want to go back to part A. So part C, let's start part C. So part C, I want to go back to part A, except I want to change the sample size to a 2000. Okay, so let's me paste this to here again. So this is what I wrote in part A, except this time I would like to change this to a 2000. Oh, actually, you know what? If I change that to a 2000, that changes the 75% too. If I change that to a 2000. So what I am trying to do is I'm trying to change that to a 2000. I will go ahead and erase that and then change that to a 2000. So now the p hat is now 2000 in the denominator. And then regarding the number of success, that is still a 150. So that means that will change the 0.75. That will change the 0.75 to. What I am looking at is I have a large denominator. Okay, let's go ahead and calculate the confidence interval first. So I need to calculate a 90% confidence interval. Okay, so go to stat and then go to test, and then you run a 1 proportion z interval. So the x, you cannot change that, but you increase the n to 2000. And then the z level is 0.90. Let's calculate that real quick. So this one is 0.065 and then 0.085. Okay, and let's keep 4 decimal places. 0.653 and then 0.847. 0.847. So this will be 6.5%, and then this will be 8.5%. So how long is that? 8.5 to 6.5. So the length is 2%, right? What about my my answer in part A? So the answer in part A is 80% minus 70% equals to 10%. So we are comparing the 10% and the 2%. So the 2% is n equals to 2000, and then the 10% is n equals to 200. Which one is longer? The answer is the one with a slower sample size is longer. Why? Here is how you interpret this. Think about this. Let's say 5 divided by 200 versus 5 divided by this. which fraction is bigger? The one with a smaller denominator is bigger, right? So when the sample size is so big, so what happened is, so when the sample size is large, so we have a large sample size, then you have a large standard error. This quantity, the one with a square root, this quantity is a large. As a result, you have a, oh sorry, not large, small. Right here, you have a small standard error. As a result, you have a small margin of error. Small margin of error gives you a short confidence interval. If you have a small sample size like this one, the 200, then you have a bigger standard error, and as a result, you have a bigger margin of error. As a result, you have a longer confidence interval, and this is true in any procedure, in any problem. This is always true. It doesn't matter what procedure you use. You talk about the z, you talk about the t, you talk about the proportion. This is always true. If you raise the sample size, then you make the interval longer. Sorry, if you reduce the sample size, it is so easy to say this wrong. If you reduce the sample size, like conclusion number 2, if you reduce the sample size, you make the confidence interval longer. If you make the sample size large, you reduce the length of the confidence interval, and this is true in any procedure. Okay, so that is the end of this problem. If you think my instruction is helpful, let me know in the comment section below. Please like the video, subscribe to my channel, and share the video for me. Appreciate your help as always. I will see you all in the next lesson. In the next problem, I would like to discuss what happened if the sample proportion is in decimal, not a fraction. All right, I see you in the next problem. Signing off for now.